Alright, hello class. In this video we're going to be talking about finding local extrema. So a couple of lectures ago what we did is we were using critical points to help us find absolute extrema, right? And that was actually kind of easy because all we were doing was finding the critical points and then plugging everything in and seeing which is the highest and which is the lowest. If you're not on a closed interval, okay, or you just want to know where your local extrema are, that's what we're going to be talking about here. Okay, so we're going to talk about how we analyze critical points as either local maximas or local minima. Okay, and we already actually have all the information you would want. We're going to sort of collect it all into what we call the first derivative test. But it really boils down to things we've already been doing. Specifically, when the derivative is positive, that means the original function is increasing. When the derivative is negative, that means the original function is decreasing. And where the derivative is 0 or undefined, that's where we have potentially turning points. All right, so analyzing critical points comes from this basis. Basically that when f prime is, say, positive, that corresponds to the original function f increasing. In other words, going up, okay, as we go from left to right. All right, on the other hand, if f prime is decreasing, okay, then, I'm sorry, if f prime is negative, I kind of jumped the gun there, but if f prime is negative, then f is decreasing. All right, and that means the function is going down. And otherwise, if f prime is 0 or undefined, then that can correspond, well, first of all, that's a critical point. And that can correspond with a turning point, a leveling off point, or something else. Okay, so like for example, if it's a turning point, it could be doing this or this. It could also be doing a sharp turn, right? That would be if the derivative is undefined, you can have a sharp turn. Okay, it could be a leveling point where it doesn't really turn, but it still has a horizontal tangent line there. Or it's something else, like it could be something like this where you have a vertical tangent line. Okay, or it, could just blow up. All right, it could just be also where the original function doesn't exist, so we wouldn't even have a critical point there. But other things can be happening in situations like this. So this is really what we are breaking things down into and using this to analyze critical points, and that leads us to what is called, say, the first derivative test. And it's called that for, I guess, two reasons. One, it uses the first derivative, and it's the first test that we have for derivatives. So it's first in a couple of ways. Okay, so what we basically do with the first derivative test is we break up our interval into separate regions, and then we can check them in each region. So let me write some of this down, and then we'll get into some examples. Okay, so here's what the first derivative test says. Here's how we set it up. So we're going to suppose that f is continuous and has a critical point at, let's say, x equals c. Okay, this won't work if f is not continuous. All right. Provided you avoid places where it is discontinuous, you should be okay, but it needs to be continuous on where we're looking. We're also going to suppose f is differentiable pretty much everywhere except maybe at the critical point, right? Because some critical points happen where f prime is undefined. So, all right, then, if f prime changes sign at c, then f has an extrema at c. So what do I mean by changes sign? Well, if at c, like let's say here's c, and from here, say f prime goes from positive on this side to negative on the other side, that means the original function f is going from positive or from increasing to decreasing, right? So going from positive to negative, so f prime positive to negative, that gives us a maximum, right? Because it's basically creating a max. So f has a max at C. Okay? Or if it does the opposite, let's say here's our C, and f prime starts negative on the left, but then on the right side it's positive. Okay, that means f is going from decreasing to increasing. So we have a minimum, right? So f prime is going from negative to positive. That tells us that f has a minimum at C. Okay? So that's the first condition, that if f prime changes sign at C, then f has an extrema at C. If not, well, then something else may be happening. So if f prime does not change sign, then it does not have an extrema. So otherwise, I'll say f has no extrema at C. So to give some examples of what's happening there, if here's our C and f prime goes from positive to positive, well, that means f is going from increasing to increasing. So some examples of what might be happening here would be like a leveling off, right? Or it could be a vertical tangent line, right? That's also possible. And you can also have it flipped around, right, to where f prime might be going from negative to negative. So f is going from decreasing to decreasing. So in this case, you could have a leveling off point, or you could also have a vertical tangent line type situation here at C. Okay? So basically what the first derivative test is doing is you're finding your critical points, and then you're seeing how f prime changes from the left to the right. And that is going to inform you of whether or not you have a max, a min, or neither. Now in practice, the key to how this works, okay, is we find the critical points, okay, and the trick is that these are the only places where f can turn around or behave in this way. Because if there were more places where that could happen, we would find more critical points. Okay, I mark this with a star here because this is really how this works. Because these are the only places f can have an extrema. Otherwise, we would find more critical points. So then, once we find the critical points, then we can split up the interval, right? So we might have a critical point 1, a critical point 2, a critical point 3, and a critical point 4. And then we can go through and check each region individually, right? We'll just check f prime in each of these regions, because in each region, f prime can only be, say, positive or negative. Because, and I know that because if it were to change somewhere in here, like if it changed from positive to negative, I would have another critical point. Okay? So we can check each region individually, and that will tell us about what's happening in the entire split that we've made. Okay? In other words, checking the regions is possible by using a single test point from each. So we can take a point from here and from here and from here and check f prime at this point, because if it's positive at this point, it's going to be positive at every point in this region. Because if it's not, well, again, we would have found another critical point here. We can test one point here and it's going to tell us what's happening in the entire region. That is the heart of how the first derivative test works. We are able to test each region using a single point because we found every other possible point where it would be 0 or it would be changing. Okay? So I think hopefully this will come together a little easier when we start looking at some examples. So let's go ahead and do that. All right. Let's begin with this example. Say we want to find the local extrema of f of x equals 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1. So to start with, we need to find the critical points. Okay, so to find the critical points, of course, we need to find the derivative to start with. So the derivative, it's just going to be power rules here. That's nice. We're going to have 12x cubed minus 12, oops, don't know why I'm writing 14, minus 12x squared minus 12x plus 12. Well, that came out pretty nicely. Now, when we find critical points, there are two things we need to look for. One, and it's the one that I think we always remember, is what causes this to be equal to 0, but also two, what causes this to be undefined? Well, nothing's going to cause this derivative to be undefined because it's just a polynomial. So really it's a matter of setting it equal to 0 and solving. So I'm going to start by taking out a 12. And so when we take out a 12, we'll have x cubed minus x squared minus x plus 1. So this one looks like it can be factored by grouping. We can take an x squared out of the first group and possibly a negative 1 out of the second group. So let's do that. We'll have, I'm going to actually divide out this 12 just so it goes away. I don't want to deal with it anymore. All right, so we can take out an x squared from the first group to be left with an x minus 1. And then here, if we take out a negative 1, then we'll be left with x minus 1. All right, so now we can factor out the x minus 1 to get x minus 1. Okay, times x squared minus 1 equals 0. All right, now this might seem a little strange, but what I'm going to do is factor this one again, because that's going to be x minus 1 times x plus 1. All right, so that's going to be x minus 1 all squared times x plus 1 equals 0. So x is either 1 from in here or negative 1. All right, so these are the critical points. All right, now, the reason I wanted to do that is because I can rewrite this derivative using this factored version as long as we keep the 12. So f prime can be rewritten as 12 times x minus 1 all squared times x plus 1. Now, why in the world would I care about that? Well, that's because now that we have our critical points, I'm going to set up a number line. Okay, so here's our next step. We found the critical points. Step 2 is analyze each critical point on a number line. Okay, now there are a few ways to do this. Some people have, different methods for doing it. I prefer to just set up a number line, and I'm going to put my critical points down. So I have negative 1, and I have positive 1. Okay, now, when we check these, you do not check them separately. Like, you don't just check negative 1 and you don't just check 1. You have to check them all at the same time, because you want to make sure that you're picking values around, for example, you want to pick values just around negative 1. And you want to pick values just around 1, but you don't want to accidentally choose something over here, like at negative 2, to check around 1. You want something between negative 1 and 1. Okay, so we have our regions here. All right, and then we're going to check f prime. And it's going to tell us what's happening with f. Now, here's the important bit that I think this makes this much nicer, is I don't really care what the values are. All I really care about is whether it's positive or negative. So here, I'm going to pick some test values. So I think maybe negative 2 would be a good test value. Here 0 would be a good test value, and here 2 would be a good test value. Okay, so here f prime of -2. Well, here's something to keep in mind. This piece, right, is always going to be greater than or equal to 0, right? 12 is always positive. Something squared is always greater than or equal to 0. So whether this is positive or negative is completely determined here, right? So this is going to be 12 times a -3 squared times a -2 plus 1, which is a -1. Right, so this is a positive times a positive times a negative, so this whole thing comes out to be negative. Okay, so that means f is decreasing in this region or going down. Okay, next region, I'm going to put in f prime of 0, so that's going to be 12 times -1 squared times 1. So I have positive, positive, positive. The whole thing comes out to be positive. So you see here how I'm not even bothering with what the number is. Sometimes I will, sometimes I won't. All I care about is whether it's positive or negative. Now that tells us that the function's increasing in this region. Okay, then finally, this third region I'm going to put in 2, so f prime of 2 will be 12 times, that will be 1 squared times 3, that's positive, positive, positive. Derivative's positive in this region as well. Okay, so that means f is increasing in this particular region as well. So what we have is that the function goes from decreasing to increasing at -1. So this is a minimum. However, here at 1, we're going from increasing to increasing. So we probably have something like that instead. So this is neither a max or a min. Okay. So f has a local minimum at x equals -1. Okay, f is decreasing. It's decreasing on this interval, -∞ to -1, and increasing. It's increasing on -1 to 1 and 1 to infinity. Some people would join these together, but I would argue that since f prime is 0, that it's not increasing or decreasing. It is stopped at that particular moment. But I don't think, I'm certainly not that picky about this. I don't know if the online homework is either. I think it will usually specify how it will want it, but this is usually a pretty safe bet. Okay, so there we go. This is how essentially the first derivative test acts. You find the critical points, you split your region into pieces based on those critical points, and then you check each region with a point you find. Find the nicest one you can, okay? And that is how it goes. All right, so let's do another one. Actually, before we move on to another example, I thought I would show a graph. We see here at -1, we do have a minimum. It turns out to be the absolute minimum because it is the only minimum we have. And then here we have a leveling off point at 1. Okay? So what we found analytically does actually align with what we found on the graph here. All right, next up, let's find the local extrema of f of x equals x to the 2/3 times 2 minus x. I didn't spend much time talking about continuity and differentiability last time because we had a polynomial. Here, though, we have x to the 2/3. Now, x to the 2/3 is going to be continuous everywhere, but we might have a critical point that is an undefined one because we're looking at a fractional. Also, since the denominator is odd, we can put negatives in here. So it's going to be continuous everywhere. It might not be differentiable everywhere, though. Okay, so let me mark that so I'm on the lookout for it. All right, so let's start by trying to find the critical points. And we can do that either by, well, of course, you have to take the derivative. That's always our first step. In fact, in this module, if you aren't taking a derivative as your first step, you might be doing something wrong. Now we can use the product rule, or we could distribute this across and use power rules. I'm just going to use the product rule here. I have 2/3 x to the 2/3 minus 3/3, which will be negative 1/3. Then times the second function left alone, then plus the first function left alone times the derivative of the second, which will just be negative 1. Okay, so I'm going to simplify this down before I start setting things equal to 0, because we will need to plug things into f prime. So when I said that later we'll have plenty of opportunities to simplify our derivatives, that's this module. Okay, a lot of times we're going to want to simplify our derivative because that's going to make things a lot easier for us as we go through. So I am going to simplify this a bit. I'm going to put this in the bottom of the fraction. So I have 2/3 times a 1 over x to the third, and then times 2 minus x. And this is just going to be a minus x to the 2/3. All right, so we'll simplify this a bit more. I'll bring the 2 and the 2 minus x up to the top. So we'll get 4 minus 2x on top, and we'll get 3x to the 1/3 on the bottom. And we still have that minus x to the 2/3. Now, I want to do some fractional arithmetic here, so I want to get this as a common denominator. So I'm going to multiply this by 3x to the 1/3 over 3x to the 1/3. All right, just to get a nice common denominator. Now this might be looking kind of gross, but we're going to see some simplification here. So we're going to get 4 minus 2x all over 3x to the 1/3. Okay, and minus, here up top, x to the 2/3 times x to the 1/3. Well, that's going to be x to the 2/3 plus 1/3, which would be x to the 1. So this is literally just going to be 3x over 3x to the 1/3. Okay? And now that we have a common denominator, we can just say that this is 4 minus 2x minus 3x all over 3x to the 1/3. All right, so f prime of x can be simplified all the way down to 4 minus 5x all over 3x to the 1/3. All right, now from here, right off the bat, in fact, we could see it right here that x equals 0 is going to cause this to be undefined. So f prime is undefined at x equals 0, because x equals 0 will cause division by 0, and it's, and that's really all there is to it. It's undefined. And it's a constant over 0, right? When we put in 0, right, our f prime of 0 is going to be a 4 over 0 case. And if we remember from our limit theory, that means that this is a plus or minus infinity. So f prime has some blow up here. So that's going to make this a critical point. All right, so don't forget these critical points that are undefined. All right, so that's the first bit. Now the second bit, we're going to set this equal to 0. So we're going to take 4 minus 5x over 3x to the 1/3 and set it equal to 0. And let me give you a quick way to tell if a fraction is equal to 0. A fraction is equal to 0 if and only if the top is equal to 0 and the bottom is not. All right, and what's important there is basically if you can get the top to equal 0 and that same value doesn't make the bottom equal 0, then that's really all you have to focus on. So here, we're just going to focus on this equation here, where x is going to be 4/5. Okay, and that's not going to cause this denominator equal 0. We've already taken care of that. So the critical points are x equals 0 and 4/5. Okay, so now we are going to make our number line. It's the way I like to do it anyway. Okay, so here I'll put 0 and 4/5. Okay, and then we have our 3 regions set up now that we're going to check. Okay, so my tests, I could do -1 in this region. Here, I need something between 0 and 4/5. An easy thing to do would be something like 2/5. Okay, because there'll be 1, 2, 3, 4/5. So just picking something you know is in between is a good way to go there. And then here, 4/5, we know that's less than +1, so we could just pick +1. So you pretty much are always just picking the smallest values you can. Or maybe not the smallest, but the easiest values you can. Maybe 1/5 would be easier here. I don't think it really matters. Okay, now, when we plug in f prime of -1, so let's plug in -1. Okay, so that means we're going to get 4 minus 5 times -1. So that's going to be a 4 plus 5 all over 3 times -1 to the 1/3. So this is going to be a 9 over 3 times -1. So this will be a 9 over -3. So that's going to be a -3. So specifically, the important part is the derivative is negative in this region. So that means f is decreasing, going down. All right. So for the next region, we are going to pick 2/3, but it could be 1/3. I'm sorry, 2/5, not 2/3. So 2/5, it could be 1/5, whatever. I don't think it's going to matter that much. But notice the 5th is going to cancel nicely with that 5. So it'll be 4 minus 5 times 2/5. So those 5s are actually cancel. 3 times 2/5 to the 1/3. So specifically, this is 4 minus 2 up top. So it's 2 over 3 to the 2/5 to the 1/3. I don't care what this is. This is a positive over positive, so it's positive. Okay, so this means that our original function is increasing on this region. So that means we have a minimum here at 0. Okay, great. And now we're going to plug in 1. Thankfully, much easier than the 2/5, but again. So f prime of 1 is 4 minus 5 all over 3 times 1 to the 1/3. So this is going to be -1 over 3, which is negative, so the function's decreasing in this region. Okay, so we're going from increasing to decreasing, so that means we have a maximum. Okay, so all right, f has a local max at 4/5 and a local min at 0. F is increasing on 0 to 4/5 and is decreasing, right, on -infinity to 0. So here, this region, and from 4/5 to infinity, this region. Okay. Right, and real quick, if we check the graph, we see here is our local min at 0. And notice it's a sharp one, and that's what we found because this was an undefined derivative here. This is where the function was non-differentiable. And then at 4/5, we have Maybe if we zoom in a little more, we might be able to get a better sense of where that turning point is. But that's a nice thing about the first derivative test is just looking at the graph, it can be difficult to tell if that's 4/5, for example. Okay, so that's where the analytical stuff comes in. All right, so that is pretty much it for this particular lesson. I mean, that is how the first derivative test works. But for the time remaining, I'm just going to do a few more, say, more complicated examples, so you see something a little maybe trickier. So what we want to do for this one is we want to find the local extrema of this function, f of x equals square root of x ln x on the interval 0 to infinity. Okay, now notice that's just the domain of this function. Since ln, you can only put positive values in. And the square root of x, you could put 0, but since you can't put 0 here, then that's, it's not going to be part of the domain. All right, so we're going to start by finding the critical points. Of course, that means we're going to start by taking the derivative. All right, so this will be a product rule. So it would be the derivative of the square root of x, which is 1 over 2 root x, times the natural log of x left alone, plus the square root of x left alone, times the derivative of the natural log of x, which is 1 over x. Okay, now you might look at this and think that we're in a lot of trouble, but here's how I would simplify this one. I have square root of x and I'm dividing by x. Well, x itself is 2 square root x's multiplied together, right? So that's going to cancel, and this actually simplifies out to be natural log of x over 2 root x plus 1 over root x. Okay, so we almost have a common denominator, right? All we have to do is multiply by 2 over 2 to get it. So now we have the natural log of x plus 2 all over 2 root x. Now, just looking at this, of course, 0 is going to cause this to be undefined. However, that's not a critical point. It's not even in our domain. Something to note, though. All right, so yes, f prime of 0 is undefined, but that's not in the domain, so we don't need to include it in our analysis. All right, so what we really just need to do now is set f prime of x, which is the natural log of x plus 2 over 2 root x, and set it equal to 0, which basically means that we're really just considering the natural log of x plus 2 equal to 0. Okay, which means we're looking at the natural log of x is equal to negative 2, and now this is where we do the bring in the e, so that we get x is equal to e to the negative 2, or 1 over e squared. Okay, so this is our one critical point in this interval. Now, when you have a restricted domain like this, when you go to set up your number line, I like to do this. I'm going from 0, but not including it. Okay, so I put it open dot, and then continue my number line here, and then I'm going to put this 1 over e squared here as our critical point. So really, we only have the one critical point, so we only really need to check around 1 over e squared. However, be sure that you pick something between 0 and 1 over e squared. All right, now if you look in your calculator, 1 over e squared is about 0.135. So for my test, I'm just going to pick, say, 0.1. There's a lot of things we could do here. I'm just going to pick 0.1 and then just plug it in the calculator. I think it's likely to be negative here, but we'll see. So f prime of 0.1 is going to be, right, that's about negative 0.478. So the important part is that it's negative in this region. So that means our original function f is decreasing. Okay? Now, something greater than 1 over e squared, well, this is much easier. I can just pick 1. Okay, so just pick 1. That's definitely greater than 1 over e squared. So f prime of 1, that's going to be a natural log of 1 plus 2 over 2 root 1. So just 2. Natural log of 1 is 0. So this is 2 over 2, which is 1. Specifically, what's important is that it's positive. All right, so that means our function is increasing. So we have a minimum at 1 over e squared. All right, so f has a local minimum at x equals 1 over e squared, and then f is increasing on the interval 1 over e squared to infinity, and decreasing on 0 to 1 over e squared. So this is how you adjust for a restricted domain. Right? If you look at a graph here, this is sort of what we're looking at, and we definitely have a turning point somewhere in here. Again, less than, so here's our 0.1, here's our 0.15, our turning point's in here somewhere. So this is where the calculus really comes in handy, because I know I have a turning point somewhere in here, but it's really difficult to tell where, and it turns out it's at about 0.135, I think it was, we found. All right, let's look at another example. Let's say f of x is equal to x times e to the negative x squared over 2. And this is definitely continuous and differentiable everywhere, because x and e to the stuff, at least this stuff, is continuous and differentiable everywhere. All right, so we're going to start by finding the derivative. Now this is going to be a product rule. So it'll be the derivative of the first, which will be 1, times e to the stuff left alone. Okay, then plus x left alone, now times the derivative of e to the stuff. So it'll be itself, then times the derivative of the stuff. So the derivative of negative x squared over 2, which will be, negative 2x over 2, so it'll just be negative x. Okay, so this ends up being e to the negative x squared over 2 minus x squared e to the negative x squared over 2, and we can factor out that e to the stuff. So let's do that. That's going to be e to that stuff times 1 minus x squared. And now, when we go to find critical points, here's something to keep in mind, is that, remember, this e to the stuff is not actually going to affect what we're doing at all. This is always positive. Okay? So when we set this equal to 0, we can just ignore this. So really, we're just looking at this. 1 minus x squared is equal to 0. So 1 is equal to x squared, so x is equal to plus or minus 1. All right? Now, we can set up our number line. It's negative 1, 1. So we need to check sort of all 3 of these regions. And I should have given myself more room here, so let me do that. Okay, so these are the critical points. All right, so to find our test values, I'm going to use, I guess, negative 2 here. I'm going to use 0 here, and I'm going to use, right, and then 2 here. Now, when we're checking whether our derivative is positive or negative, notice this e to the stuff part is always positive. So we can actually kind of ignore that and just see what this is doing. All right, so f prime of negative 2, well, this part, right, the e stuff is always positive. This part is going to be a 1 minus 4. So that's going to be a negative. So this whole thing in this region is negative. So that means our f is decreasing in this region. All right, so next up, we're going to plug in 0. So f prime of 0 here, well, again, we have something that's positive, times a 1 minus 0. So it's a positive times a positive. So this whole thing is positive. All right, so that means our original function in this region is increasing, meaning we have a minimum here at -1. Now let's check f prime of 2. So f prime of 2, we have that piece that's always positive, and then we'll have the 1 minus 4 again. So since we're squaring here, that's what causes this to be negative again. So we have a positive and a negative, so that's negative. So this region, the derivative is negative, so the function is decreasing. All right, so we have a minimum at -1 and a maximum at +1. Right? Decreasing to increasing, increasing to decreasing. All right, so that's that. I'll leave it to you to write out in words what's going on here. All right, but real quick, here's the graph. And as we can see, we have a minimum at -1 and a maximum at 1. Okay. So, I think that is definitely enough to get you all rolling on the homework. Again, there are many different types of functions out there that we can apply to this, or apply the first derivative test to. I can't go over every single type, but hopefully this is enough to kind of give you an idea of how it all works together. And in the next video, we're going to start looking at what the second derivative does for us. All right, so I'll talk to you all on that one. Cheers.